Hello, I'm Sonic. We will learn about hyperboloids. A hyperboloid is the surface obtained from a hyperboloid of revolution by deforming it by means of directional scalings, or more generally, of an affine transformation. Also, a hyperboloid of revolution, sometimes called a circular hyperboloid, is the surface generated by rotating a hyperbola around one of its principal axes. You are familiar with the formula of hyperbola in two-dimensional. That is x squared by a squared, minus y squared by b squared, equal to 1. In three-dimensional, the formula becomes x squared by a squared, plus y squared by b squared, minus z squared by c squared, equal to 1. Note that the minus sign is along with its axis. If we ever say minus z squared by c squared, that means the hyperboloid is in z-axis. Similarly, we can ever find out for the x and y-axis, as the negative sign is present. If all the signs change, that is minus x squared by a squared, minus y squared by b squared, plus z squared by c squared, equal to minus 1. This equation is called an imaginary hyperboloid. There consists of two types of hyperboloid: hyperboloid of one sheet, and hyperboloid of two sheets. In hyperboloid of one sheet, when all the pair of lines rotate, you'll notice that each pair of line can twist itself by increasing its length. One point is fixed at each end, and the other point moves at the other end. If a maximum length of a line is obtained, you'll notice it's like a shape of two cones, at a phase of 180 degrees. Also, to find out intersections, just like in cones that you are already familiar. If a plane intersects along x and y axis, you will notice the intersection of hyperbola. If a plane intersects along z-axis, you will notice the intersection of circle. If we ever find the intersection of ellipse, either the plane has tilted at an angle for the first option, or the aspect ratio of hyperboloid has modified for the second option. On the other hand, the hyperboloid of two sheets made with two paraboloids. The intersection can be done in same way just like in one sheet. But what happens when intersection between two sheets is applied? The plane must touch at least on a surface to obtain a point form either for the first, or the second ones. Between two sheets without touching them, thus, no intersection is obtained. So these are the two types of hyperboloid. But one thing for the application. For example, St. Louis Science Center's James S. McDonnell Planetarium, located in St. Louis, Missouri, and was constructed in 1963. This features a thin shell and hyperboloid structure, that is one sheet. That is how the two types we have discussed for the hyperboloids. Like, comment, and subscribe now.